Today I want to show you how we can solve this differential equation up here. So if you look at it at first glance, maybe it seems a little complicated, but we can actually use the method of the integrating factor to solve it. So I'm going to do this. I'm going to move 4y to the left hand side of the equation. So we're going to have x times dy dx minus 4y is equal to x cubed cosine x. Now, perhaps this is something you can identify as a first order linear differential equation, and maybe you can see how the method of the integrating factor can be used here. So we have a first order derivative and y. Something we can do is, well, we can multiply by an integrating factor and then use the derivative of that integrating factor times y to find y, okay? Now, if you haven't seen the method of the integrating factor before, if you haven't seen it before, I guess what I just said doesn't make much sense, but let me show you what I meant by that. So we need to isolate dy dx, and by that I mean we need to have it as a single term. So I'm going to divide both sides of the equation by x, and that's going to give us dy dx minus 4 divided by x, this is a 4, minus 4 divided by x times y, and this is equal to x squared cosine x, okay? So I just divided both sides of the equation by x. Now, the method of the integrating factor works like this. You're going to multiply both sides of the equation by a factor. Let's say that is k. So you do k here, and you also multiply the right-hand side by k. And k, well, it's going to satisfy this property. So let's say, let k be equal to a function of x such that, so you see such that the derivative of the quantity k times y is equal to the right hand side of this equation, which is k x squared cosine x. Now, if this is the first time you see this method, you may think that I just pulled this out of thin air and that how is this going to work? Well, let me show you. We do this, we want to find a k that satisfies this equation because we can do something pretty smart. We can integrate both sides of this equation above with respect to x. So we can take the integral of ky, the derivative of ky, with respect to x, and this is the x. We have this, right? Now, notice what happens here. We have the derivative of ky, and we're undoing the derivative. So we're going to have ky is equal to the derivative of kx squared cosine x dx. Now, our goal is to find y, and notice that if I divide both sides of this equation by k, I'm going to have that y is equal to 1 over k times the integral of kx squared cosine x dx. Okay? Now, by saying that we want a k such that this is true, we can write this formula. Okay? And notice that the only thing we need to do to find y at this point is to find k. Okay? And that is actually very easy to do using this equation here. Let me show you. So we're gonna now continue and differentiate this part. Now, if we differentiate that using the product rule, we're gonna have dk dx times y plus, we have k dy dx, and we know this is equal to kx squared cosine. However, we know this expression is also equal to this left-hand side of our differential equation. So I'm going to write k dy dx minus, and we have 4k y divided by x. Now this is wonderful because notice that we can cancel out a few things. First of all, k dy dx, so this goes away, this goes away. Now we're going to have dk dx times y is equal to minus 4ky divided by x. Notice we have two y's, the y's go away. And now we have dk divided by dx is equal to minus 4k hope you can see that this is a separable differential equation, which is what I said before. We want to find an integrating factor that allows us, or an integrating factor that is computable through a separable differential equation, okay, which is what we have here. So now we can solve for k and then plug it in here by just solving this equation. So I'm going to divide by k on both sides. So we have dk divided by k is equal to minus 4 dx divided by x. And I'm going to integrate both sides of this equation. Now this is going to give us ln of the absolute value of k, and this is equal to minus 4 times the ln of the absolute value of x. And there's a constant of integration. However, typically we let this constant be equal to 0, okay? Because in the end we're going to have another constant and everything will work out nicely in the end, so we just let this be equal to 0. So now if we're going to find k, we just have to exponentiate both sides. So I'm going to write an e here and then just say that we're exponentiating the entire equation. And we have that k is equal to, so we have e to this value. So this is the same as if we were doing e to the ln x, and the absolute value of ln x, although we're going to drop it in a moment. So I'm not going to write it. If we exponentiate this, it's the same as if we had this, and this is the same as having 1 over x to the 4th power, okay? So our integrating factor, k as a function of x, is this, okay? And now the only thing we have to do is just simply plug in k into this equation for y and then solve for y. So just to use the space that I have, I'm going to continue on this side here. I'm going to continue over here, I think. Actually, no, over here, yeah. So we have y is equal to that. Now let's just simply solve for y. So we're going to have y equals 1 over x, 1 over k. So that is going to be y is equal to x to the 4th power times the integral of k x squared. So it's going to be x squared divided by x to the 4th power times cosine of x dx. And we can continue writing this as x to the 4th power times the integral of cosine x divided by x squared dx. Okay, sweet. Now this is the equation that we get in the end, and I had to go back and check if this has an analytical solution, and I believe it does not have an analytical solution, so we can leave our answer like this. However, I believe most people would try doing an integration by parts in this case. Now let's try doing that real quickly, and then I think you're gonna trust me that there is no analytical closed form solution for this equation. So something you could do is you could say, remember, maybe you don't remember integration by parts, but the idea is that the integral of uv prime is equal to uv minus the integral of u prime v, right? So if you try to match this form to this, well, we have cosine x, so we can say v prime is equal to cosine x, and that means that u is equal to 1 over x squared. Now, that means that we could rewrite technically this this integral like this. So we could say the integral of cosine x divided by x squared dx is equal to uv. Now u is going to be 1 over x squared, and v is going to be sine of x. We just integrate cosine x. So this is sine of x divided by x squared minus the derivative of u. Now we know that will be minus 2 divided by u to the 3rd power, okay, which is the derivative power rule, and then times v, which should be, oh my bad, I mean, that's not u. This is an x, sorry, hopefully you caught that. And we have this, and then we have times, that would be v, which is sine of x. Now, for our purposes, yes, maybe there are some tricks you could do to find a series to represent this, but for our purposes, this is our final solution. There is no way you can write this in any simpler form. So this is our solution to our differential equation, okay? And what's important is that something I think I should highlight is if we're able to compute a derivative, an integral, sorry, in this part, you're gonna get a constant of integration, and you need to be sure to multiply that constant of integration by x to the fourth power, okay? It is very common to make the mistake that, it is very common to think that, oh, that's a constant of integration, whatever I do to it is just gonna give me another constant. No. If you multiply a constant of integration by x to the fourth power, you're gonna have c times x to the fourth power, so watch out for that. But overall, yeah, I would argue this is our final solution, okay? So I hope you enjoyed this video, I hope you learned something, and I hope to see you in the following one. Bye.